In the previous video, I demonstrated the positive effects of genetic exchange on evolution. It's easy to implement genetic exchange in unicellular organisms with things like horizontal gene transfer. But multicellular organisms complicate things. Evolution's response was to divide organisms into two biological sexes. It also created a lot of independent mechanisms of sex determination. In animals, it is the females who make the greatest contribution to offspring. However, one female can produce a limited amount of offspring during their lifetime. Meanwhile, one male can impregnate a potentially unlimited amount of females. So the most rational choice is to make a male-to-female ratio skewed on the female side. Let's look at these examples. In the left population, the male-to-female ratio is 1:1, while in the right it is skewed on the female side. The second approach is more beneficial. That means evolution should strive for a female-prevailed sex ratio. But surprisingly, the equal ratio is more common in nature. Equal sex ratio is so common among animals that most people never wonder why. This seems strange, especially when you consider that polygamy is widespread in animals, meaning only a small number of males participate in reproduction. The rest are left behind in the evolutionary process and only waste resources. By the way, polygamy strengthens competition among males, which causes the development of odd and hypertrophied features among them. But this is a topic for another video. Humans, like most mammals, use the XY sex determination system. It sustains an equal sex ratio by design. But it doesn't answer why this is the way. A system with fewer males would be more rational from an evolutionary standpoint. So let's discuss why an equal sex ratio is far more common in the natural world. Equal sex ratio is an evolutionarily stable strategy. This means any fluctuations are inevitably suppressed by natural selection. This phenomenon was first described by Sir Ronald Fisher in 1930. Now it is known as Fisher's principle. Let's assume the population is stable and the male-to-female ratio is 1:4. Then in the next generation, male organisms will pass their genes to 5 offspring, while for each female there will be 1¼ of organisms on average. So in this population, males have a huge advantage. If a mutation that makes it more likely for offspring to be male occurs, then an organism with this mutation will have significantly more grandchildren. Many of those grandchildren will also inherit the mutation. It will quickly spread in the population. It will stop only when there are more males than females. At this point, leaving female offspring would be more beneficial. This is just negative feedback that will try to achieve an equal sex ratio. Note that while equal sex ratio is not a rational strategy for the population itself, it is an evolutionary stable strategy. Math fans can probably remember Nash equilibrium. The main thing to understand is that evolution and natural selection are not always optimal and rational from a human point of view. Now let's try to see it in a simulation. In this simulation, each organism has a gene representing its chance to leave a male offspring. The gene is a digit in the 0 to 100 range. When two organisms engage in reproduction, we sum their chances to leave a male and divide the sum by 2. The result is the chance for offspring to be male. In this particular case, the chance is 60%. Offspring inherits a gene from one of its parents. But this gene can mutate and its value will shift a bit. One of these genes will be inherited by an offspring. At each new step, we create a new generation. We chose a random male and a random female to create an offspring. This is a program I've created to run a simulation. In the first generation, each organism has a gene with a value of 10. This means the ratio of males in the population is 10%. The sex ratio value is shown here. Blue color marks males, green females. In the center, you can see how the sex ratio has changed over time. At the bottom, you can see a histogram of the distribution of different gene values in the population. The average gene value in the population is shown here. You can see that due to the negative feedback, the sex ratio quickly achieved equilibrium. The distribution of gene variance is gradually moving from normal to uniform. When the sex ratio was equalized, the offspring's biological sex became irrelevant. Organisms can produce only daughters, as long there's an equal amount of sons from other parents. The average value of the gene in the population is 50, which means there are 50 males per 100 new organisms on average. Yet, if we look separately for each sex, we can see that males shift towards a higher probability of producing a male, and females have the opposite. This is easy to explain. Organisms with a high value of the gene are likely to have a male offspring that will inherit this high-value gene. For organisms with a high chance of producing a female, the situation is the same. The simulation will come to the same ratio if we initially make more males. That is, the model works as intended and shows why the sex ratio always achieves equilibrium. Even if we reduce the population size, the result will be the same. However, the system will be less stable. This is just the law of large numbers. The bigger the population, the easier it is to predict how it will develop. Now let's try to play a bit with the parameters and see how error-proof the model is. What happens if every lucky male mates with 1,000 females, leaving the rest of the males without a mate? Usually, polygamous species have from 2 to several dozen females per male. 1,000 females are way too much, but it hasn't affected the system significantly. If the sex ratio is equal, each female will have 2 offspring with a chance equal to 1. The average male will have 2,000 offspring with a chance equal to 1,000. Either way, the mathematical expectation is equal to 2 offspring. If the balance shifts in one direction or another, one of the sexes will gain an advantage and the equal ratio will be restored. Let's make that so only one male per generation will participate in reproduction. The system broke, and the sex ratio value changes are completely random. This is a slow process, so I've decided to speed up things a bit. The gene value in the population follows the value of the gene in the current alpha male. However, in the long run, the sex ratio will be equal on average. Let's go back to monogamy. Let's assume that now only female gene value matters in determining offspring's biological sex. Yet the negative feedback keeps the sex ratio equal. But if we look at average gene values, we can see a few curious details. The average gene value among the females is 50. This value determines the sex ratio. However, among the males, the average gene value is unusually high. They produce offspring with the same high value. But most of their offspring are males, which doesn't affect the sex ratio. The same situation occurs when we make males able to determine offspring's biological gender. So far we haven't been able to circumvent Fisher's principle. But let's keep trying. Let's return everything to the initial parameters, when both parents determine offspring's biological gender. But what if offspring will always inherit only its mother gene? As a result, the population now has less than 5% of the males. Why is this happening? Males are rare and being one is beneficial. A female with a high probability of producing a male will have many grandchildren. However, her grandchildren will not have the gene increasing the likelihood of producing a male, since it is inherited only from the mother. If we make offspring inherit only the father's gene, we would get the opposite situation. But if we make it so that the biological sex of the offspring is determined by one sex, and the gene is passed from the other, then again we see a tendency towards an equal sex ratio. However, the process is quite slow, so I've decided to speed up things a bit. When describing Fisher's principle, I've omitted one crucial detail. Fisher said that the principle only works if the cost of producing offspring of any sex is equal. If male reproduction is more expensive than the same number of females, then the sex ratio will be evolutionarily biased towards female dominance, and vice versa. Let's model this. In this simulation, producing male offspring is expensive. This is implemented by making a female able to produce several children, but after giving birth to a male she won't be able to produce offspring anymore. Let's start the simulation. With the set conditions, the male-to-female ratio is stabilized at 2:3. But this is just the beginning. The value in the gene begins to tend to extreme values. I was unable to determine the cause of this effect. I would be glad to see your thoughts in the comments. There's another strategy we haven't discussed yet. I'm talking about hermaphrodites. In a population of such organisms, each specimen can produce offspring while still having all the advantages of sexual reproduction. It seems like the most rational strategy. Hermaphroditism is fairly common in plant life but is extremely rare among animals. Maybe there's a simple explanation for this phenomenon, but I again couldn't find it. Feel free to write your ideas in the comments. That's it for today's video. Special thanks to all my patrons on Patreon. Your support allows me to create and research more interesting projects. Till next time.